All right, let's have a look at the navigation system I've implemented. All the pathfinding logic is contained in this one pathfinding script. What it does is generate a big grid of points, which is controlled by a node radius like this, if you want to change the size of the nodes, and a grid size if you want to have more points. With these controls, you can be as detailed as you want. All the points are currently green now, which means that they are valid, that the agents can walk to them. I have this max walkable angle, which I can decrease if I want to. And as you can see, when I decrease this, it'll make the points that are on angled surfaces, such as this, it'll make them inaccessible or blocked. So the pathfinding algorithms will not consider them when searching for a path. When deciding what node to go to next, it decides which node it should go to based on one or two costs. First cost is how far away the next node is from our current location. And the other one is how far away the point is from the target location. I can also choose to increase the costs for straight, like for example, this one or this one, this one, this one, compared to the diagonal, which is diagonal points like these on the corners. So those are the costs that my algorithms use. And the algorithms that are implemented to actually find the path, we can see here under pathfinding methods. I've implemented breadth first search, best first search, depth first search, Dijkstra, and A star. Let's use A star now as an example. Now let's enable debugging for our path so we can show the path. Boom. Now it will show the path generated from our current position to the target position. When I move the agent, you can see that it finds a new path in real time, and it also avoids the red blocked circles or the points. If I also enable show search to nodes, the debug will show us all the points that have been searched while finding this path. A star does a great job here. There's not many points being searched. If I change this to, for example, depth first search, you can see that a lot more points are being searched. And also if I disable the search nodes, so I only see the path generated is also a super complicated and way too long path. So we can scroll through these and see which algorithms does the job. Pretty much all of them does a great job, except depth first search, which just like some sort of inverse stuff. A star is definitely the fastest and best one though. I can also choose to only allow straight movement, so it will not go diagonal if we want that kind of behavior. We also have two mask settings in our script. We have an unwalkable mask, which defines where I cannot walk, and I also have a walkable mask that defines where I actually can walk. My landscape here has the walkable mask, and this cube has the unwalkable layer, which means that when I drag this onto my nav grid, it will block the path generated. So we'll find a new path around it. Another feature of our navigation system is what we call weight zones. It's a prefab with a script attached to it. This has a simple weight cost, which when changed will choose how much weight is added to each node. This weight affects the cost of movement to the node. So you can see when I increase it, the navigation system suddenly decides that, you know what, it's actually faster to go around it. If it's a lower value, I can move it around, and you can see that sometimes it chooses to go around it, and sometimes it will just go through it either way because it's cheaper than going around it. When the path is generated, a simple function is called by the nav agents. So when I press play, the agent walks along the path across the world and reaches its target. Here you can see our game map using this navigation system. As you can see, the river here is set as a water, which in our pathfinding script is set as an unwalkable layer. Therefore, it will block those nodes. We also have weight zones in the forests. That makes it harder to go through a forest than just walk around it. Let's disable the grid display. And as you can see, the Pokemon are walking around the world using this navigation system. So to summarize, a highly modular system which uses a lot of parameters to let the users decide how their navigation grid is made. And also, we have several different pathfinding methods, so you can choose which one fits your project the best.
So, hi, I'm Tom. I'm going to talk through my contributions to the project, which was on top of all of the gameplay stuff on the learning side of the AI. So, bringing you to the code first, there's three main classes that were used for the neural network itself. What was implemented was a feed-forward neural network using backpropagation to learn, and all that's contained within this lovely neural network class. Some of the parameters of this are just the network shape and the learning rate, which then gets passed through to each of the layers. So yeah, the neural network class itself is just responsible for calling the specific functions in each of the layers. So it's got functions like train, which call feed forward and then back propagate to help the neural network learn. It's got compute, which just spits out an output from an input. And then it's obviously got feed forward and back propagate as well, which calls the responsible back propagation function for whether it's an output layer or a hidden layer. And here's the layer class. The layer class has a bunch of different parameters and also some different activation functions. And you can see that each of the layers, take them in as a parameter and initialize based on that. It's a feed-forward neural network, so it's responsible for passing values through and then passing the error rates back to adjust the weights in order to learn. It has these two functions here, evaluate and derive, which call the responsible activation and derivation of the responsible functions for the neurons. So we've got tan H, sigmoid, and ReNeu, which are in there. So in terms of where they're actually used within the project, well, we've got two we've got two implementations of it. We've got our type learner, which is responsible for telling us whether a type is immune, neutral, super effective, or not very effective against another specific type. And it does this by having a neural network per type that it's trained, and then it just gets the value from it. Then we've also got the move decision learner, which spits out whether it should attack, switch, or heal, depending on a variety of inputs. So the move decision learner itself comes from actions that the player did. So I set up some code to record every single action that the player does when in a Pokemon battle, and that spits out a massive CSV that looks like this. And there's one of these per battle. So you can see I've got rather a few on here, 213 on my machine alone. So obviously this data can't be used by the neural network straight away. So it gets fed through a Python pipeline and spits out some normalized data that looks a little bit like this. This is the actual data that was used to train the AI. You can see it has about 8 inputs and 3 outputs, and with the outputs being whether it should attack, switch, or heal. And that's all based on the player data, as I said. So the other data for the neural network, for the type, comes from splitting up this data here. And this data here is what's used by the actual game logic in order to determine how much damage an attack should do, depending on the specific types. But of course, this data can't be used straight away. So what we did is we split up each of the inputs based on the types, and then we normalized it to just true or false values, depending on the type. So you can see here we've got 17 inputs and then 4 outputs, depending on whether it's immune, not very effective, neutral, or super effective. Both of these are used by the Pokémonster trainer class within the game to inform the decisions that the Pokemon trainers use when you battle them. Again, the key decisions are whether to attack, switch, or heal. And then depending on which one of those, it uses the type advantage one to determine which attack it should use, which Pokemon it should switch to, or whether it's worth healing, or whether it should try and attack to try and to gain the edge over the opponent. So you can see here in the switch Pokemon one, for instance, it loops through all of the Pokemon, and then it grabs, it finds the Pokemon who is the most effective, who has the most effectiveness against the player's Pokemon, which is cool stuff. Yeah, so I'll just show you this in action. I'll run over to, you start out with a random team of Pokemon, and then I'll run over to one of the trainers that I know has a semi-decent team, so that I can show you this, hopefully a battle in full. So underneath here, let's have a look at what Pokemon I've got. That's a decent mix. So yeah, I'm going to stay with my Voltorb out straight away, because I know that Voltorb is super effective against Pidgeot. The AI is only as good as its training data, and because we've only got about 600 entries to the Move Decision Learner's training data, sometimes it is a bit stupid, like it's deciding to heal straight away, even though it's at full health. So we've added a little bit of C# logic to the outcome of the decisions to make sure that what it does actually makes sense. So here, for instance, we only tell it to heal if it has less than half health, and it's made the heal choice from the neural network. So yeah, here it's decided to attack instead, and it's chosen to use move swift, which is neutral against me. But I'm going to try using thunder. Oh, I thought Pidgeot was a flying type, but maybe I'm confused. I'm going to use Thunderbolt. Yay, Pidgeot was paralyzed. I'm going to heal up, and then I'm going to try and take this dude down. Oh, I missed. Okay. And you can see on the left-hand side that it's choosing to attack. If I swap out to someone, do I have anyone who... Okay, I don't have anyone who's super effective against Pidgeot, so I'm just going to kill it. There you go. And it's decided to send out Raticate, since that was the best choice against it. What I'm going to do is I'm going to swap out to Ghastly, who's a ghost type. So I know that Raticate is immune, so he should decide to switch at some point here. Oh, he decided to kill me. What did he do? He used Pursuit, which is a duck type. It was super effective. Okay, great. I love getting beaten by my own AI. Right, okay, let me send out someone else. Okay, so he's decided... Again, he keeps deciding to heal him. I'm not sure what is causing that. I'm going to try and kill him. Oh, what am I doing? Attack. Keep it drain, please. Nice. Okay, so you saw that it's now decided to send up Ninetales. Ninetales is a fire type, which is super effective against my Vileplume, who is a grass type. So I'm going to swap out to a water type now. And we should see, yep, the AI has immediately decided to switch. So if I go and attack with a water type move, oh, okay, it decided to send out Pikachu, who's an electric type, which would be super effective. Pikachu's quite a weak Pokemon though, and he died straight away. So he sent out Gengar. So again, he's not sending out the Ninetales, even though it's probably the strongest Pokemon on this team that's remaining. He's not sending it out because he's got that type disadvantage. So sticking with Gengar, I'm going to try and sludge bomb him. Let me heal myself up, and then let's try and take him down. There you go, Gengar fainted. So again, he's not sending out Ninetales, he's sending out Kangaskhan, he's a normal type, so I'm going to heal. In fact, I'm going to swap out to someone who might be a little bit more effective. I'm going to send out Omastar. And let's see if I can H and Power. Oh, okay. He decided to use a super effective move against me. Yeah, I like getting beaten by my own AI. That's a great feeling. Let's see, Thunderbolt. Oh my goodness. Okay, I didn't realize he had... That's another super effective move. Oh, if I get beaten by this is really embarrassing. Okay, let's use Giga Drain. Yeah, let's heal up. Let's use Solar Beam. Okay, great. Let's use Steel Wing. Let's heal up. And he decided to heal up there as well. He was below half health. He decided that the best outcome would be to heal. So he decided to heal up, which is what I would have done in his situation there as well. So good for the AI. I hope I can kill him because he looks like he might be able to take me out. Otherwise, oh, he decided to heal. Brilliant. Or attack. Pursuit. Oh, okay. Oh, brilliant. Okay, amazing. Yeah, I think I'm going to get beaten by this. Yeah, I did. There we go. You can see, it's a fairly decently capable Pokemon battler because it beat me at my own game. Yeah, again, it's luck of the draw really because you're obviously given a random team, but yeah, you can see that most of the time now it was making the best decisions, especially when it was deciding to heal. And the best bit as well is, every battle that happens, it records the data so that we're able to train the AI to be even better. But yeah, that about sums it up for all of the learning side of things. Yeah, cool.
So this is the flocking section of the video where I will be showing each of the flocking mechanisms as long as the game doesn't freeze. So there's the two different types of flocks. We have the ground flock and the aerial flocks, which can be adjusted using the sliders to the right. So if the avoid is maxed out, then the flock should, over there, I believe is flock 1. They are as spread out as they can be, whereas flock 2, which is the one in front, is condensed. If the alignment is set to the maximum, and they're also cohesive, then they should be trying to align as well as they can to the leader. If they are set to avoid, Might be better to show. Yeah, so they're trying to mimic the leader. All of the vectors for this are all calculated here, where it will find the rotation and the actual movement is calculated here using each of the vectors calculated underneath, and it will calculate the best direction to avoid to make sure they don't collide. It will also calculate where the neighbors are located, so it can also use this information to avoid them as best as possible. All of this is used here to allow for each bird to spawn and have their speed set, everything's assigned properly, and all the birds are set to whatever flocking unit has been set, which the flocking unit is determined by what has been set here, as the birds are all set to being a Pidgey, and all of the retarders are set to being a rat. All the Pidgeys have flapping animations set by Emil, and they have been dotted around the world a little bit in various locations. You can see them.